I should maybe move this here. There is the exterior, which we have heard a lot about in Martin, Sergio, Peter, both Peters actually talk. And so the black hole exterior is an object that's now relatively well understood. And then there is this region, the black hole interior, in which infalling observers fall, and that region is much less understood. So what I want to ask today is what happens in the interior of a dynamical and, let's say, generic black hole. So that's what I want to discuss. And I will start first by telling you about the work of Roger Penrose and his celebrated singularity theorems. So this theorem came under the spotlight recently because that's thanks to this theorem that Roger Penrose was awarded a Physics Nobel Prize in 2020. And in a sense, this is a beginning of the story of the interior of black holes. Okay, so we'll start with discussing these theorems and their implications. In the second part of the talk, I will tell you about one of the biggest open problems in the field, which is the so-called strong cosmic censorship conjecture. So we heard a little bit about it. It was mentioned by Yakov in the last talks. And one of the key properties in the black hole interior relevant to strong cosmic censorship are so-called Cauchy horizons. So I will discuss what they are and what are the consequences of the existence of these Cauchy horizons on the conjecture. Then I will tell you about a phenomenon which concerns the black hole interior, which is the fact that the stationary solutions are unstable. So that perhaps comes as a surprise because we heard a lot about black hole stability, but all the talks about black hole stability were about the exterior of the black hole. And in the interior, in fact, we have an instability. And even more interestingly, in fact, this instability is physical, and we can track down what is the endpoint of this instability, in particular on regarding the Cauchy horizon. So I will tell you a bit about that. And finally, I will tell you about a phenomenon which I discovered in my work, which has to do with the global aspects of the black hole interior. And what happens to this Cauchy horizon, which already suffers from a local instability globally? Well, something very dramatic. The Cauchy horizon has to break down. So I will explain what this means and how we can prove this in the framework of spherical symmetry. So that's going to be the plan for the talk. And so if I'm going to talk about black holes, I don't resist starting a talk on black holes. I don't resist presenting the Schwarzschild metric. So the Schwarzschild metric, first black hole ever written, doesn't need any introduction, I think. What I want to talk about, so it's a stationary solution, of course, that's well known. What I want to talk about is the interior of the Schwarzschild metric. So perhaps a lesser known aspect of this metric. And specifically what happens to observers. So this would be this green curve, observers that enter the interior of the Schwarzschild black hole. And so what happens is that this observer here in green, in finite proper time, will encounter a singularity. So that's a singularity at I equals 0. And it is a particularly strong singularity in the sense that not only the curvature blows up, but also the tidal deformations blow up for this observer. So the tidal deformations, it's something that doesn't live at the level of curvature, it's more of the level of the metric itself. So if you want a sort of blow up of the metric in amplitude, that's one way to see it. Okay, so that's a case of Schwarzschild. But Schwarzschild is not so physical, perhaps, because it does not rotate, and we expect that black holes rotate. So to understand a black hole that rotates and that's still stationary, we have to jump back almost 50 years and to Kerr, 1963. So we have this Kerr metric, still stationary, has a mass and an angular momentum. It can be written very explicitly. Let me not do this here because the expression is a bit complicated. And it's a solution also of the Einstein equations, like Kerr. And it also has a simpler cousin, which is the Reiser-Nordström metric, written much earlier, which is this time a black hole that has a charge. Okay, so this is much simpler to write. It's like the Schwarzschild metric and has a charge term here. And why am I writing these two black holes on the same slide? Well, the point is that they have the same, or at least very similar, geometry in the interior. So what's happening in the interior of these black holes? They have what's called a Cauchy horizon. So what happens is that you still have observers that enter the black hole. This is this green arrow here, okay, and this is still finite proper time. So this is an incomplete geodesic, okay. But here the observer does not encounter any singularity. So it's perfectly smooth, okay. So this is in complete contrast with what happens for Schwarzschild. Okay, this time there's no singularity, even though there's still incompleteness of geodesics. There is no singularity whatsoever, and you can attribute that to the fact that if you look at a black hole with momentum, this slows down a little bit the gravitational collapse because of centrifugal forces. If you have electric charge, that also slows everything down because of the repulsive effect, and that's why both this charge and rotating black hole have a very similar geometry. Okay, so that's something that's going to come back during the talk also. So we have these three examples of black holes, and back in the early 60s, in 1963, I think it's fair to say that a lot of physicists didn't really believe in these black holes. The point being that these black holes, they are yet other exact solution of the Einstein equations. They have many symmetries. They are stationary. In other words, they seem very contrived. Okay, and they could be just mathematical artifacts of the theory. And it was really a revolution when Penrose came with his result and told us that no, we should think of black holes as something robust in a certain sense. So this revolution came from the singularity theorem. So Penrose assumes a very soft condition, which is a positivity of the energy. So essentially that this tensor is positive when contracted against null vectors. So in particular, this is what happens in vacuum. And then the theorem says the following. If you have a trapped surface, compact trapped surface in the space-time, then you have geodesic incompleteness. And why is this important? It's important because the condition of a trapped surface, we've seen this in many talks this week. The condition of a trapped surface is that some quantity has negative trace. Okay, trace is strictly negative. So this is an open condition. So it means if you perturb something that has strictly negative trace, then by very soft argument, you know that this condition will be stable. So these black holes that we've seen before, they have a trapped surface. If you perturb them, of course you will still have a trapped surface. And so by the theorem of Penrose, then you also have geodesic incompleteness, which was interpreted at the time as some form of singularity. So this was really a key statement that convinced a lot of people on theoretical grounds that black holes should be real objects. Okay, should be at least stable to perturbations, at least on this heuristic level. And indeed, it is this result that is credited to Penrose for his Nobel Prize. And the citation of the Nobel Prize says that black hole formation is a robust prediction of the general theory of relativity. So needless to say, that's a beautiful story, but that's a story that's a bit oops. That's a story that's a bit incomplete. Okay, so this is without no pun intended. The point is that geodesic incompleteness, in fact, doesn't really mean that there is any kind of singularity. Because come back to short sheet, okay, true, there was a singularity, okay, incompleteness and a singularity. But for Kerr, for example, there was also incompleteness, right? And yet no singularity. So what it means is that perhaps this groundbreaking theorem of Penrose, one of the first theorems in Lorentzian geometry, perhaps it doesn't carry the correct name. Perhaps instead of a singularity theorem, we should call this, it's maybe more proper to call this an incompleteness theorem. And if this is just an incompleteness theorem, then this leaves the following question open. Is there even a singularity in the interior of a dynamical black hole? And does a dynamical black hole more look like Churchill or more look like Kerr, where there is no singularity? So this is a question that I want to in the following parts of the talk. So to address this problem, you have to perturb black holes, which is something that we know how to do. To do this, we have to introduce the initial value problem. So take the equations, okay, and put some data at time equals 0. Okay, so Cauchy problem, time equals 0, R3. Okay, so you have your data. Okay, you have your second fundamental form K0. Okay, and you can construct the maximal solution for the maximal globally hyperbolic development of this data. Okay, this is something that's been well known since the 60s. Okay, and that's a correct framework to talk about any stability problem. So, so to do this, to investigate what happens when you perturb black holes, maybe you want to start with data at time equals 0 that is close to a Kerr metric. Okay, and then in a certain norm, okay, that depends on the context. And then you will evolve such data and try to understand what is the geometry of the resulting black hole interior, and in particular, whether there is a singularity or not. So now this becomes a problem of a prime in hyperbolic PDEs, and you need to do this through quantitative estimates. Okay. So you can do this. You can do this in vacuum. You can also do this in spherical symmetry. So that's a simpler problem. But if you want to do it in spherical symmetry, you can't do this in vacuum because of the rigidity of vacuum in spherical symmetry, called Birkhoff theorem. So I would claim that there is a sort of canonical model, okay, to quote Yakov, about scalar field. Okay, in the same way that scalar field was canonical for Crusoe, let me claim that a sort of canonical model to say this prime in spherical symmetry is the charge scalar field with a Maxwell field. Okay, so what's the point in that? The point is that even though it's in spherical symmetry, so there is no momentum, the effect of charge is kind of a substitute to angular momentum, following the good advice of John Wheeler. And indeed, this model or very similar variants to this model that were studied in the literature by really many authors. Okay. Depending on the context, maybe there's some small variations, but essentially these are models that are based on scalar field. And the idea is that if you're in spherical symmetry, then the gravitational degrees of freedom that you lose from the Einstein equation are recovered by the scalar field. Okay. So this model, okay, as far as we know, this is the best. This is the best, at least as far as I can tell, to study this prime in spherical symmetry. And this is what I will consider in what follows. And now, of course, you have to make the necessary modification, prescribe more data for the Maxwell field and the scalar field. And instead of starting next to Kerr, you will perhaps start next to horizon nostrum. Okay. So let's consider this model, and of course, whether you do it with or without spherical symmetry, this problem has two parts, and they obey very different type of analysis. The first part is the exterior of the black hole, and that we've heard of this a lot in Martin Stokes, Sergio Stoke, Peter as well. The exterior of the black hole. The point is that stationary solutions are stable, and the main mechanism is the dispersion of waves. So now it's a prime that's quite well understood, and in fact, so I apologize if I couldn't cite everyone, but these are some recent contributions. There were many also earlier contributions, both in the mathematics and physics literature. So that's for the exterior. For the interior, it's completely different in that, as I said in the beginning, the stationary solutions are unstable this time. And so from the point of view of PDEs, it's a completely different game. It's not going to be wave dispersion that's going to be the main phenomenon. It's going to be the formation of a dynamical singularity inside black holes. Okay, so singularities have to be dynamically formed in a sense. And that's why you also cannot save yourself from doing the Cauchy, the dynamical problem, if you want to understand black hole interior. Okay, as will become apparent when I tell you a bit more about the results. So having said that, now the real point of focus in the talk, in understanding the black hole interior, will be to understand, is there a singularity in dynamical black holes? And if so, how strong is the singularity? So this would be related to the strong cosmic censorship conjecture that I already mentioned. So let me introduce that conjecture now for you. So the question you ask yourself is, what does it mean for general relativity to be a deterministic theory? The same way that if you throw a stone in the air, you know that the motion of the stone will be determined through the Newtonian theory will be determined by the initial position and velocity. Well, similarly, what you can do is that you can take initial data at time equals 0 in general relativity. So that's something we already know how to do. Okay, G0 and K0. Okay, and then you can construct the maximal globally hyperbolic development, as we discussed before. And the idea that goes back to Penrose. So it's a younger Penrose, Penrose back in the 60s, is that you cannot extend that. Okay, so if you had an extension here, okay, that would not be allowed. So what's the point of this of this claim? The point is that if there were to be an extension, then that extension would not be determined by the data, because the maximal globally hyperbolic development tells you already the maximal space-time to be determined by the data. So that should be it. There shouldn't be anything else. It should be inextendable. And so, okay, so that's the conjecture of Penrose. So here, a bit of an anachronism. I hope you forgive me for that. Okay, Penrose didn't really discuss how regular this extension should be. That didn't really appear historically in the work of Penrose. Now, mathematically, we also adding the fact that it should be inextendable as a suitably regular Lorentzian manifold. Let's say CK. And the hope is that the reason why such extensions are not permitted is maybe if there is a singularity here, a singularity of side of regularity CK, okay, in the metric, that would make the extension forbidden. But at this stage, I mean, this is only wishful thinking. This is really, there's nothing, you know, that suggests that this could even realistically be true. And in fact, it's even worse than this. If you think about this conjecture for a second, you wonder why the conjecture is not completely silly. The point is that we have this black hole that we mentioned before, the horizon nostrum and Kerr black hole, And remember that the Kerr black hole, at least, is quite physical because it's a stationary rotating black hole, right? So it should describe in some regime sort of end state of a black hole. And yet it has this Cauchy horizon that was perfectly smooth. And the problem with that is that because the Cauchy horizon is smooth, it means that it can be smoothly extended. And in fact, it's not only that, it's that it can be smoothly extended. So seemingly being a counterexample to the conjecture, and this extension is widely non-unique. Essentially, this extension can be anything you want, basically. Okay, so based on that counterexample, it seems that the conjecture is not very reasonable. It seems that we have a counterexample, but maybe it's still okay. It means that all data cannot respect determinism, but after all, maybe almost all data respect determinism. The point is that a black hole would never be exactly stationary, right? Stationary black holes consist of a very, very small subset in the set of initial data, that a subset that is highly non-generic. And in fact, this issue was quite well understood to Penrose himself, who writes the first paper about strong cosmic censorship. I managed to dig this one out. It says, it is not completely clear to me, it is not completely clear to me that a black hole is ever exactly stationary. Okay. So that means it's not a very reasonable model to request the black holes to be exactly stationary. And so that means that this counterexample, we can maybe deem it as something non-generic and still have the conjecture preserved for generic initial data. And in fact, this is something that Penrose already understood. Okay, so that I didn't really emphasize it, but this was already part of the conjecture. Okay, but of course, it means that in the analysis, this is going to considerably complicate the analysis because now it means that we have to prove statement not for all data, but only for generic ones. So okay, that's fine. We still hope to say something about that. So as I said earlier, the model that I would consider in the rest of the talk is this spherically symmetric model of a charged scalar field. And remember what's the motivation for that? It's the fact that charge plays a role of angular momentum. And because I want to understand the interior, I will take data on the event horizon. So this is my data, H+. Here I have a bit of an ingoing surface, okay? I take my data here, okay? This is V equals infinity, okay? And I'm gonna solve towards the interior of the black hole here. This is the interior and that's the exterior, okay? So because I want to put data on the event horizon, I need to choose to prescribe this data. And of course, I'm going to prescribe this data in a way that is consistent with the convergence towards the stationary solution, because remember that the exterior is stable, right? So that's equivalent to requiring some decay on the scalar field, in fact. Okay, as v tends to infinity, let's say the scalar field that is here, I request it to decay. Okay, and this is consistent with the issue of tails that have been discussed both in the talk of Jonathan Luke and also the one of CU1 Mark. Okay, you have decay, dispersion of waves, and that you can say it's a generalization of Price's law. Okay, this is polynomial decay. Okay. But there is one difference with what we had in the talk of Jonathan Luke and CU1 Mark, is that in this model, the decay you expect is extremely slow. So the decay is S is less than 1. And for all of you who have experience in nonlinear PDEs, you would know that when you have very slow decay, nonlinear effects become important. And indeed, this is what happens in this problem. And because nonlinear effects are so important, you may hope that they would destroy this Cauchy horizon. Okay, so you would hope that perhaps the Cauchy horizon is destroyed when you turn the nonlinear problem. The Cauchy horizon would be unstable. And that would be great if that was true. That would be great for the sake of determinism. So that's the hope that we're entertaining here. And in fact, this was realistically entertained for a very, very long time in the physics literature, up to 2005 at least. Okay, but it's quite a borderline. It's quite a borderline case that, in fact, sadly, this doesn't happen. So Cauchy horizons are unfortunately stable to perturbation, even though the decay is so slow. Okay, so you assume some decay, and that's extremely slow, barely better than 1 over the square root of v. Okay, still you can show that the Cauchy horizon is stable. So that sounds like bad news, of course. But there is still hope if you want to save strong cosmic censorship. There is still hope because Penrose condition has nothing to do with Cauchy horizons a priori, right? Even though they are an obvious obstruction, it has to do with extendability. So you can consider the issue of inextendability, which is the simplest possible, where k equals 0. Remember that the conjecture is that you have ck inextendability. K equals 0 means continuous inextendability. That's the simplest, the strongest, and to be honest with you, probably the only one that was considered in the physics literature for a very, very long time, because it doesn't impose to take derivative. You don't have to ask yourself too many questions if you look at C0, let's say, inextendability, at least if you entertain that hope. But even that, in fact, sadly, is not true. And for this model, it's not true for a very unexpected reason, which are oscillations. So the point is that you take a scalar field which decays so slowly that essentially you can't say anything in general. So it decays so slowly that this integral is probably infinite, the L1 norm. So it's not, the profile is not integrable. Nevertheless, it is semi. So nevertheless, we will take data that is oscillating in the sense that it's semi-integral. Okay, so that's the result we obtained with Christoph Keller, who's at IAS. And what the result says that if you take such data that's oscillating, despite the slowness of the decay, you can show that you have continuous extendability. Okay. And you have boundedness in a very weak norm, which is a C0 norm. Okay, so the solution is bounded. And so you may ask, how realistic is this assumption on the event horizon? Well, I would argue quite realistic, because in fact, numerics, so that's not something that's proven mathematically, that's certainly interesting to look at. Numerics have shown that the scalar field does have some oscillation on the exterior of the black hole, in particular on the event horizon. So you have very slow decay, a power that's less than 1, but a sinus with a non-zero pulsation here. So you can check that for such a profile, indeed, this condition is satisfied. Okay. And the outcome of that is that while the Cauchy horizon is being continuously extendable, that means that the C0 version of Penrose's strong cosmic censorship is false. And as unfortunate as it is, we have to live with this. And I also want to emphasize that this mechanism of oscillations, as far as I can tell, this is not something that was ever discussed in the physics literature. So it's something that came really as a surprise to us when we got that result. And last comment about this result is that in fact this result is also sharp. So that, okay, I didn't mention here, but let me say we also prove in the same paper that if you do not have oscillations, meaning that if this becomes infinity, then you can negate all the statement in a certain sense. Okay, so you cannot really avoid looking at oscillations if you want to solve C0 strong cosmic censorship in this setting. Okay. So now, this is a picture we have, and let me also say that even outside spherical symmetry, at least in vacuum, we know, and that's a very beautiful result by Thermos and Luke, we know that this result is still true, that the Cauchy horizon is continuously extendable. But the mechanism is a bit different, because in vacuum you can assume you have faster decay, and because you have faster decay, then oscillations don't matter in a sense. Okay, so the mechanism is is completely different for vacuum, but at least the result is still true. It would be very nice to try to do this result as well outside spherical symmetry and see what you can say when you have very slow decay. Okay, so let me give a little digression. Okay, now following up with the beautiful talk of Gary Horowitz. So in this framework, what happens if you don't assume slow decay, but you assume no decay at all? So phi doesn't tend to 0, it tends, let's say, to a constant. Okay. So when that happens, it's a situation that's physically very interesting. This is what we call a hairy black hole, and this was well understood numerically by Gary Horowitz and collaborators in various contexts, and mathematically. So in a simplified setting, you can show the following. So if you start with data, let's not take it to tend to a constant. Let's be even more drastic. Let's take it to be a constant. Okay, we think it's reasonable to think it's stable, but okay, let's be simple. Let's take a small constant on the event horizon. Okay, like this, and let's start with the Rising-Nordstrom metric. Then the theorem tells you that well, you don't have a Cauchy horizon. In fact, you have a strong space-like singularity here. Okay. And the singularity where I equals 0, you also have a blow-up of curvature like an inverse power of R. So so let me make some comments on that. Okay, it's a bit surprising because this metric is a charged black hole. Okay, and yet it has a space-like singularity. So as far as I know, there doesn't exist other charged black holes that have this property, where the singularity is everywhere space. As far as I know, but if you know an example, let me know. This is all the more surprising. The metric we perturb is Rising-Nordstrom, and it does have a Cauchy horizon and no singularity at all. And note that, of course, this is completely different than the case where we have decay, right? So if we have decay, phi tends to 0 in a certain sense. Then remember we have stability of the Cauchy horizon. So that's a completely different scenario. And the other thing that's very strange, and that's why the paper is called violent nonlinear collapse, is that you see this curvature. This curvature gets more singular as epsilon tends to 0. So when epsilon tends to 0, this rate becomes infinite, and so in fact the solution becomes more singular. It's kind of the opposite of what you would expect. You would expect that if epsilon is small, then you're closer to the thing you perturb, and the singularity is milder. No, it's in fact stronger. Okay, and that's because there are very nonlinear dynamics that are being involved in this result. Yes. So if you measure, so yeah, that's a great question. So first of all, let me say that measuring in R is still something geometric because it's the area radius. But if you measure in proper time, then this will be a standard Kastner singularity. Okay, with however degenerating exponents. Okay, so there's also something interesting happening with the Kastner exponents. What's interesting in this and what's behind this is that there is a huge discrepancy between proper time and area radius. That's kind of the origin of all of this. Yeah, that's a great question. Thanks. Okay, so that was a digression. Okay, so I just wanted to mention that since we had this beautiful talk on hairy black holes earlier this week. Now let me come back to the main story, which is determinism and strong cosmic censorship. So we have seen that we have this Cauchy horizon, and C0 strong cosmic censorship is false. So you may say that well, perhaps we need to give up on determinism after all. But that may be a bit too quick in bearing determinism. The point is that there is an instability mechanism on black holes, which is quite simple. It's just for the linear wave equation, and that was already understood by Penrose, and many mathematicians have then proven theorems about that and make this very rigorous, and that's called the Blueshift instability. And what it does essentially is that maybe I should say that on the on the tablet. So what it does that it shows you that when you have a signal that goes here, okay, essentially the frequency becomes infinite, shifted to the blue infinity. Okay, so you have this mechanism, and we haven't talked about that yet. So the question that now is open is what happens to the nonlinear setting to this instability, and does it influence the geometry of the black hole, particularly the geometry of the Cauchy horizon? And the answer, perhaps not so surprisingly, is that it does. And the beauty of it is that this will be the redemption, the longer-weighted redemption of determinism, and this will allow us to vindicate Roger Penrose and his strong cosmic censorship conjecture. So to summarize what was already said, we have this very desirable version of determinism, which was to not extend as a continuous metric, but as desirable as it is sadly false. Okay, so we're going to do the next best thing, which is the C2 strong cosmic censorship. So why C2? You're going to tell me why not Holder, why not H3 or whatever. Well, the point is that the equations live at the level of two derivatives of the metric. Okay, so if you can't extend as a C2 Lorentzian metric, then that means you can't extend as a classical solution to the equations. So I would dare say that this is quite a national class to look at. And again, the hope for this to be true would be to say that there is some blow up of curvature or some form of C2 norm in the interior of the black hole. Okay, and again at that stage it's purely wishful thinking. But it turns out to be true, in fact. So for this model, so start with same assumptions as before, so slow decay, and also make the assumption of a lower bound. So remember the discussion, we had this discussion in the talks of CU and Ma. After the talk, you need lower bounds for instability, right? Also in the talk of Jonathan Lopez. So you need lower bounds to show instability. So we made that lower bound. That just basically says that, well, you just want polynomial decay, right? You don't want this to be exponential, let's say. Okay, it's an upper bound. Okay, you need a corresponding lower bound. And if you ask yourself, what do I have to integrate? Well, it's just because remember the type of profile I have, or I expect at least, is something that oscillates. So I don't want a pointwise lower bound because that wouldn't be true, right? Sign is 0, right? So doesn't have pointwise lower bound, but if I have average, then there is a chance that this be true. So now what the theorem says, let me clean a little bit my slide. What the theorem says is that you do have the instability, okay, in higher Sobolev norm. So we know that we have stability in the C0 norm, right? But in the H1 norm, you have blow up. So take a point of the Cauchy horizon, take a compact set, integrate the gradient, okay, and it yields infinity, okay. And the consequence of that instability is that the metric has infinite curvature in a certain sense, and is inextendable as a C2 Lorentzian manifold across the Cauchy horizon. So the conclusion of that is that at least for 200 data, it's kind of a big restriction, I'll discuss that later, but at least for 200 data, the C2 version of strong cosmic censorship is true. And I also want to emphasize that this conclusion was already reached for a simpler model, the uncharged massless scalar field by Luke and O in 2017, which is prior to the work to my works. And let me just for those of you who know this paper, let me just explain a bit the differences. So here you have the Cauchy horizon here, okay, and the way the proof goes is that you start with a local analysis. So you start with a local analysis here, okay, in a small rectangle, and then you try to extend, okay, to something global, okay. And so here in the uncharged setting, you do the local argument, okay, and that's also what I do here, okay. So the local argument is quite similar in both papers, and in fact, so my result is very inspired from what's done by Luke and O. And then for the global setting, you can argue by monotonicity. Okay. In the charged scalar field setting, which has more terms, you don't have any monotonicity. So then you need to do a global argument separately, and that's what's being done in the next paper. Okay, so that's kind of the reason why there are two papers and not one to deal with this issue. Okay, so that's what happens. We have this singularity. It's only a weak singularity though, because it's only the H1 norm or the C2 norm of the metric that blow up. Okay, so the singularity is only weak in that sense. So, okay, so that means now we have understood basically everything there is to understand about the local geometry. So if you look at what happens on the Cauchy horizon, you have a Cauchy horizon, but it's singular, so you can't extend. And in a sense, the reason why we could conclude strong cosmic censorship from this, so strong cosmic censorship is a completely global problem, okay? But the reason why we could conclude that is because of a small cheat, okay? The cheat being that in spherical symmetry, you can only have a Cauchy horizon or a boundary where I equals 0. If I equals 0, then you know you can't extend, okay, by a soft argument. So in spherical symmetry, we can conclude strong cosmic censorship in this setting, completely bypassing the global. But if you want to understand strong cosmic censorship with no assumption, you need to understand the global structure, obviously. So and understanding the global structure is anyway a very important problem in the dynamics of black holes. So so that's what I want to discuss now, trying to understand the global structure of black holes in spherical symmetry. Okay. So so what do I mean first by the global structure? Well, the global structure will depend, as you may guess, on the global data you put here, right? So you need to put some data. What's a bit striking about that, and I'm sure this will speak to the geometers among us, and maybe to the geometer that lives inside each of us, is that it only depends on essentially on the topology of said data, okay, and nothing more essentially. So that's what I want to explain now, the sort of unexpected occurrence of topology. And for that, we have to understand this role, we have to remember what black holes are. So black holes physically, they are formed from the gravitational collapse of a heavy star. And so what's a star? Well, a star, it's a space-time that has a center, okay? A center where I equals 0, okay? So let's declare that to be a star, okay? And in a sense, okay, if you want to study gravitational collapse, this is the only reasonable thing you can study, and this is related to issues in topological censorship that I'm happy to elaborate about, but let me not say too much about that. So what does it have to do with topology? Well, if you have I equals 0, then that means that you have an origin, so your topology in spherical symmetry at least must be that of R3, the sort of boring topology, for instance, the trivial topology. This is in contrast with Kerr and Reiser-Nordström, which have a much stranger topology that is given by something like I'm trying to draw two ends here. So here there is one end first of all, and here there's one. There are two ends. Okay, so one here and one here. Okay, so I equals infinity. I equals infinity. I really apologize for the terrible drawing. As you can guess, you know, I wasn't close to becoming an artist. Okay, so so the difference, so that's Kerr, Reiser-Nordström. The difference is that the radius here is non-zero. Okay, so you have a throat. Okay, you have two ends. Okay, and then the radius here is lower bounded. Okay, so it doesn't have a center. So what does it mean? Well, it means certainly that Kerr and Reiser-Nordström are very poor global models for black holes. Okay, we already know that the interior is not a great model because it's unstable. Okay, but as a sort of global gravitational collapse spacetime, this does not do a good job. Okay, so we have to Of course, they can still locally describe the black hole, but globally, we really have to embrace the correct topology, which is a topology given by R3. And of course, this is this is hard, and that's why it was only done by a handful of authors, albeit quite famous authors, starting by Oppenheimer and Schneider. But very few people have studied the sort of global aspect of the black hole in this setting. So in the folklore of the physics literature, this is an old problem. But I think the person who really narrowed it down in the mathematics is Mihalis de Thermos. And so the Thermos problem, and I borrowed these slides from I think 6-7 years ago, Stephen Hawking birthday conference. So the Thermos problem is as follows. So you have some understanding of the formation of Cauchy horizons, some local understanding. And the question is what happens globally. So if you have one end, okay, so that's the setting we looked at, okay, gravitational collapse. Can you have potentially an additional boundary piece in the space-time? Okay, that's what the Thermos says. Or can the Cauchy horizon close off the space-time, so to speak? So what does that mean? The Cauchy horizon close off the space-time? It means a Penrose diagram that looks like this. Okay, so here you see you have your center of the star. I forgot to say that I equals 0 was the center, and this is this boundary. Okay, that's the center. I equals 0, and it would meet with the Cauchy horizon at this point. Okay, so in that sense, it closes out the space-time, okay, so to speak. Okay, and so that's a priori perfectly plausible. And so what I did in my work is that I solved that Thermos problem in spherical symmetry, and show that this can in fact never happen. Okay, and I also gave the mechanism that's behind this, and that mechanism is a breakdown of the weakly singular Cauchy horizon. So let me explain the assumption of the theorem. So exactly the same as before, essentially. Okay, and now just make an additional one, which is a global one: the existence of a regular center. It's a completely soft assumption. It just means you take your data here, okay, and then here you meet I equals 0, and let's say the metric is is C1, something like this. Okay? Something very, very soft, something very mild, okay, but global nonetheless, because it has to be global. Then the result is that the Cauchy horizon cannot close off the space-time, and more rigorously, what it means that there exist boundary points. So rigorously, that would be terminal indecomposable paths, but if you've never heard of this, don't worry. So there exist boundary points essentially that are space-like. Okay, and what does it mean? How do we define space-like here? Well, we define space-like by saying you have a boundary point. If you take the path cone like this, okay, the intersection with the data here is compact. Okay, that's how we define the boundary point to be space-like. So there exists at least one boundary point that is space-like. That's the statement I want to make. And so, in fact, it's quite nice that we know that the fact that gamma is not empty, this assumption is necessary, because the Thermos has actually looked at the 200 case. So you remember the case that was not so physical, okay, the 200 case, okay, but nevertheless interesting mathematically, in which gamma is empty, and he has showed that, in fact, the Cauchy horizon can and does close out the space-time, at least in certain region, okay? So in fact, this theorem, you really need to take the whole topology into account. It's a very global phenomenon. And it's a global phenomenon, and it's also non-perturbative instability, because there's no stationary black hole in the picture, right? After all, okay? The only stationary black hole we have is Reise-Nordström, that converges to Reise-Nordström in this region. But away from that, there's no stationary black hole to converge to. So you may ask, what is the end state of this instability? And that the theorem can also answer to partially. So you either have the option that the whole of the singularity is crushing or space-like, okay? I equals 0, so that's what you expect generically. Or you also have this other option that the theorem cannot exclude, is what's called a locally naked singularity. So this were mentioned a little bit also. I believe in Yakov's talk. So the point that it's not naked because it's not outside a black hole, but it would still be seen by local observers inside the black hole. Okay, so you can still have this abnormality, okay, locally naked singularity. But if you believe in weak cosmic censorship, or sort of strengthened version of weak cosmic censorship, locally naked singularities should not be generic. And in fact, Christodoulou proved this in the case where you don't have any charge. Okay, so there's really no reason to doubt that the proof that it will still work when you have a Maxwell field. It's an interesting problem, but in a sense, conceptually, it should still be the case that when you have charge, then this conjecture remains true. And so, assuming this weak cosmic censorship in quotation marks, okay, that's a big if, of course. But if you assume that, then you understand everything there is to understand about spherically symmetric black holes. Okay, you understand that you have this Cauchy horizon, which is weak, that breaks down, gives this strong singularity, and as also a byproduct, which is nice, you prove the C2 version of strong cosmic censorship for one-ended spacetime, gravitational collapse. So that's the result. So to summarize, actually many results, the full picture of black holes in spherical collapse. So only the blue statement remains to be proven. All the rest are the theorems that were presented. So there is a Cauchy horizon. Sadly for determinism, it's stable. It is continuously extendable by means of oscillations. But fortunately, there is a curvature singularity here that makes it a weak singularity. And thanks to that, we can't extend. So C2 strong cosmic censorship is true. Then we need to exclude local singularity, locally naked singularity in a certain way. Okay, so let's hope we can do that. And once you have that, you can show that the Cauchy horizon has to break down, and the rest of the singularity has to be strong. Okay, so this is strong. So there is coexistence of the weak and the strong. Okay, let me just take 1 minute to tell you a bit about further open problems outside spherical symmetry. It's needless to say, it's very important to do this also outside spherical symmetry. Less is known outside spherical symmetry. The only thing that is known, that's the remarkable paper that I mentioned by Thermos and Luke, is that the Cauchy horizon exists and is continuously extendable in vacuum. But the difference is that the decay is very fast in vacuum. And so oscillations play no role. It would be very nice to try to understand what's the role of oscillations when, let's say, you have a charge scalar field outside of symmetry. Then second problem would be to understand that there is a weak singularity forming on the Cauchy horizon. And this, again, given the progress that we've seen, both from Luke O, Schlapenter-Rothman, and from Zbierski recently, gives me good hope that this problem will be solved soon. This other problem, which is to show that the breakdown is locally stable, okay? So that's a very difficult problem, but I hope I come back to a future conference and tell you more about this problem in a few years, okay? This is to show that if you look at this local region here, then it has to be stable to perturbation, okay? Non-spherically symmetric perturbations. So that's a problem that has many difficulties that I can tell you about if you're interested. And then a sort of global, the sort of dream would be this global statement that would answer everything, says that all the Wigner singularities have to break down, but that is a much more ambitious and distant research goal. Okay, so that was a lot, but I hope that this gives you an overview of the beautiful problem that are in the black hole interior, and the very exciting prospect that there are also for the future. Thank you for your attention.
Thank you. Right, so questions, I guess. Yes, Jonathan.
Yeah, maybe I can ask something. Can you go back to the main breakdown theorem, the statement? Yeah, so I wonder how seriously you use the assumption. So there's to say, if I have something that decays much faster, let's say exponentially, but maybe still consistent with the Hawking mass blowing up, do you think
that's an excellent question. So in fact, the beauty of the theorem is that you don't use that much actually. So the point is that so you need to use that the mass blows up in a sense. Okay, so that's a sort of sufficient condition. Yeah, so I didn't say that right. So it's a sufficient condition, but it's not necessary. So in fact, you can also it's also in the paper. You can prove that the Cauchy horizon breaks down even if you don't have a weak singularity. Okay, and all that you need, in fact, let me make a drawing. All that you need is that there is a tribe neighborhood of the Cauchy horizon. So you have the Cauchy horizon here, okay, and you need that there is a tribe neighborhood there of the Cauchy horizon. Okay, which is obviously something that happens if you have a mass inflation, if you have a weak singularity, but it can happen in plenty other scenarios as well. And so in the context where you have a positive cosmological constant, then you still have, I think, a trap neighborhood, and the proof works. Okay, so I didn't manage to prove that quite, but I think that's true. And if you can do that, then you can show that indeed you still have breakdown. In the case where you have lambda negative,
so you're saying that you don't even need the mass to blow up? Is that what you're saying?
That's correct. Yes, that's correct.
So you can even have a piece which is like exactly rising nostrum.
So yeah, so no, that you can't have actually. So yeah, that's every time you nail exactly the point. So here the point is that you need to have a phi not completely zero. Okay, so and that's hidden. So that's why I said here. Okay.
Oh, sorry. Okay.
Yeah.
Okay.
Yeah. So that's yeah. You really nailed the exact point. So you need these two things. Yeah, you need these two.
Okay. I see.
Yeah. And what's nice is that there is a case. So there's been some numerics for lambda negative. Okay. And so that's Pandya and Pretorius, and they show a theorem that's consistent. So for lambda negative, in certain regime you have a mass inflation, and then mass inflation you have breakdown. That's fine. There are some regime where you have no mass inflation, but the Cauchy horizon has a tribe neighborhood, okay? And then they show again it cannot close, you have breakdown. And then they have a third regime, very close to extremality, where there is no tribe neighborhood of the Cauchy horizon because the apparent horizon does something like this, okay? So this is, the Cauchy horizon is in the regular region here, okay? And in that issue, they show that the Cauchy horizon subsists up to the center. In fact, so it's something that's probably much more general. In fact, that's than what I claim. All you need is are very very weak conditions to prove that breakdown.
I see. Just one more question. This Pandya Pretorius, they also have so in 2+1 they also have a radial symmetry or not, or is it, do they have symmetry in that the
yeah, it's also, yeah, I think it's also in symmetry.
Okay, I see. Yeah. Okay. Thanks. Very nice.
There's something in the chat. I don't know.
Oh yeah.
I don't know if that's.
Scroll down in the chat.
If you want to, because I don't. Okay.
I guess I had a little quick question. Can you go back to your comment about weak non-singularities? I think the second pepper, two peppers, I think it was. Yeah, no, you're going too far. It's just no, it was the end of your talk. The two peppers.
The pepper, the chilies.
The peppers, chilies. Yeah.
I see.
Not paper, but pepper. Yes.
I see. Sorry.
So you're saying that this is the closest thing, that's the least spicy, the most attainable?
I think so. I mean, because there's been some work. I mean, as I said, okay, there's been some work. There's been that famous loop. There's been.
Can you just make? Can you just state like what you mean exactly by these things, like weak null in this context and rotating? What does that mean?
Well, it would be like if you take it. Yeah, I mean. I'm not. To be clear, I'm not involved in these works. But I think the statement would be to say that if you look at a perturbation of Kerr, okay, that decays to Kerr, you assume Kerr stability, and then you would show that you have a weak null singularity, and you have a weak null singularity on the horizon generically.
Yeah.
making some assumption. You will make some assumption on the.
But what's the precise nature of weak non-singularity in this context? Like what's the weakness exactly? Do you know? Or is there like a known, or is there a guess? Or?
Yeah, that's a very good question. So here, presumably, you maybe still have blow up of the Hawking mass, but presumably you would want something a little bit better than that. But maybe we should ask Jonathan what's the correct.
Yeah, so I think the expectation here, I mean, for the vacuum, it would be something that the metric is well, it's continuous, but really sort of no better. So it's not in any C alpha, and maybe it's in W11 and again no better. Sort of, it's not in any W1P.
Right, but what's the quantity that blows up? Because it's not. So in spherical symmetry, you have like this Ricci VV, right? But now it's Ricci flat, right? So what?
Yeah. So one thing you would think it's well, you would think certainly the Crackman scalar would blow up if you want a geometric quantity.
Or the Crackman scalar.
But you would imagine some sort of Biesky type argument would tell you that even you can say something like holonomy blow up. Maybe even that's true.
Yeah. Okay. Yeah. Fair. Yeah. So against Crackman scalar. Yeah, because Crackman scalar blows up in particular if the mass blows up. So in the Hawking, so in spherical symmetry. So since the Crackman scalar blows up, on all this spherically symmetric solution, there is a hope that this is still true outside spherical symmetry. But as I said, I'm not involved in that work. So best to ask the experts.
When you're talking about local here, are you thinking of, say, one piece of your initial data might be already living in, already have, the assumption of spherical symmetry, but then you have some relaxation of that assumption on another piece of the data?
Yeah, so you would take something that's already formed, okay, spherically symmetric, okay, take data there, okay, that correspond to the already formed one, and then give a non-spherically symmetric perturbation. Yeah, I guess that would be the problem. And already there are all sort of things that can happen, because already, so here it's something maybe I haven't emphasized, but these are spheres on the Cauchy horizon, and they collapse to a point now, okay. Now, if you do that outside spherical symmetry, then you have ellipses, and now it's not exactly clear they collapse to a line, they collapse to something degenerate like caustic, So already, that problem, you have many very interesting things to understand about that problem. And then, the global picture, is extremely ambitious.
There's a hand also by Sion Ma. Yeah. Please go ahead.
Maxime. So for your when you talk about this Einstein-Maxwell massive scalar field, I think you're assuming some lower bound. You're assuming some upper bound of decay, and then some integral equals to some integral L2 integral along horizon is infinite. Is finite or infinite, right?
So it's it's whatever. Yeah. So here you see it's in L2, right? But it's something more complicated than that. So it has. So that's the assumption, right?
Yeah. Okay. So for this, I just want to know if there is any result towards this direction, improving this lower bound of decay or sharp bound of decay, or even just a decay.
Yeah, so decay, so I didn't have the time to talk about that, but actually I've worked on this. So I have a result where I show that if the charge is sufficiently small, then you get arbitrarily close. So actually, that's an excellent question. I also have a slide for this. So so here the point that the decay you expect is very strange here. So it's so here price is low, would be S equals 3. Okay, now it depends on the charge. It's something very complicated. Yeah. It's in a sense, the scale critical thing, right? So it depends on the charge. And so in the theorem in 2018, actually proved something that's arbitrarily close to sharp. If you assume that this constant is small, okay, then I get to almost v to the minus 2, which is what
okay.
This is small. I'm also working on having sharp upper bounds and tails. So with Gadic, so we have obtained that for a toy model, and that's a paper that's going to appear very, very soon. A toy model on Minkowski, and we're also working on the case of Reise-Nordström as well, which I think will appear either this year or next year as well. Okay, so it's a sort of different flavor than the sort of wave, the wave equation when the potential folds out like 1/r³. This time it's more like 1/r³, and that's why the decay is weird.
Sure.
That's for the case of
but
charge.
what
with
about
no
the
mass.
massive case?
The massive case is even more tricky. So the massive case, so by the way, everything I said in the talk holds either for massive or massless, okay? And perhaps, you know, the massless charge case is maybe the one I want to emphasize the most. But you're right, massive is also very interesting, and even less is known, I think. I think so for the massive, the massive, the rate would be v⁻⁵. Okay.
Yeah,
that's,
some numerics, yeah.
Yeah, from
Is
numerics.
there any result towards this decay?
No, not that I'm aware of. Not that I'm aware of. Yeah.
Okay.
Yeah, that's quite interesting, I think. Do you know anything?
Okay, I see. No, not at all. But I know a paper by Finster, Yao, Smaller, Carmen. I mean, they have a paper about Dirac field on Kerr-Newman, I think, massive Dirac field on Kerr-Newman, and they show some local decay. I think that's T to the minus 5/6.
Oh, interesting. Okay.
A very old paper. I think it's 2006 or so. Yeah.
Okay, I didn't know this paper, but I look it up. Thanks.
Yeah. You can look at it if you like. Yeah.
Yeah.
I think they argue that that should be sharp, but it's local decay, and I think they trade it for modes.
I see.
Yeah. Thanks.
Thanks.
All right. Well, if there are no more questions, let's thank Maxime again.